So next we have Dr. Stefan Horn, who will talk about the City Climate Information Services.
Yes, thank you very much. I will share my screen. One moment, please. I hope you can see the presentation now. Fine. So my name is Stefan Horn from the Meteorologics AG. We are a kind of a sub business of Kachelmannwetter.com, and we are in this project responsible for the modeling. And what we try to do is that we want to provide city climate information services with our new 100-meter resolution UltraHD weather model. It's actually a weather model, so I would like to at first present a short history of the UltraHD model, that you get an idea what kind of a model it is and what is the capabilities of the model and so on. And then I will introduce the services we provide with the model and give a short outlook on the possibilities that are further development and so on. And the model UltraHD is a new implementation of a model called Asam GPU that was developed by myself about 10 years ago at the Institute of Tropospheric Research in Leipzig. And the UltraHD is an implementation using the so-called OpenCL language, which is a programming language used to let the model run on GPUs, on graphic processing units, or as they are now called, also AI processors. And in the beginning, we started with the simulation of the so-called stratocumulus clouds, as you can see illustrated in the left picture here, where we have a 3D visualization of such clouds. So this was a theoretical test case where we simulated shallow convection above a marine boundary layer and the aerosol dependence of this cloud system. So the model has a two-moment cloud microphysics within it. And later on, I also used this model for a simulation of a deep layer convection, so a supercell simulation, where we extended these two-moment microphysics from this warm cloud physics to also include ice and snow and cold ice phases and rain and so on. And this is a nice visualization. You can check it out on YouTube if you like. So we started with a convective model of moist atmospheric boundary layers. It runs on GPUs. This is some picture of such GPU. So here you can see such a server, which includes two of these GPUs currently. So for the CityCLIM project, we have two of these servers with two GPUs each. And we use every GPU for one pilot city, so to say. And compared to ordinary hardware such as CPUs, GPUs are much cheaper, more energy efficient, and also faster than CPUs. Later on, this kind of boundary layer model was extended with the so-called immersed boundary condition approach. That means we have these grids where we calculate our atmospheric state. And in every grid cell, we can parameterize kind of a pressure gradient to simulate obstacles like mountains or also buildings if we increase the resolution a lot. And these images are examples from one of our experimental nests in the Alps. And you can nicely see such a valley and how the clouds are kept in the valley by an inversion layer. And the clouds are getting more dense near the afternoon, for example. And this is to show that the model is capable of modeling such orographic flows within structured terrain. And during the CityCLIM project, you also had the opportunity to extend the model with chemical equations. So we added prognostic variables for some of the most important compounds of atmospheric chemistry, like the nitro oxides, ozone, OH radicals, and so on, and also particulate matter with 10. And the equations we use describe the attraction of these compounds, the formation, and also the reactions between those compounds up to some kind of sinks like these nitric acid and so on. And the initialization and the boundary conditions for such model ones with these pollutants are taken from the ECMWF CAMPS service. So it's a Copernicus service, which describes current states of the atmosphere with respect to these compounds. Some more technical details with the UltraHD for the ones that may be interested in this deeper knowledge. So the model itself is an explicit time integration of the compressible Euler equations. So it's a UltraHD simulation model with a very small time step. It includes the 2-moment microphysics, so for warm cloud processes and also cold cloud processes like ice and snow and so on. We have this immersed boundary approach to respect obstacles like mountains or buildings. And the model is capable of providing a deterministic forecast of the following variables like entropy, momenta, densities of the different atmospheric compounds and particle number concentrations and so on. And what we also did during the CityCLIM project, it allows us to further extend the model with a so-called soil model and a 3D radiative transfer model. So what we added was a soil model consistent of up to, I think we had 4 to 5 layers in the soil now, where we parameterize the ground heat and moisture fluxes for every grid cell. And in addition, we have this 3D radiation approach for the short and long wave radiation, where we have a 3D ray tracing approach, where we follow the rays to the sun and integrate the liquid water and the water vapor part and so on, and parameterize the downward short wave radiation and also the outward going long wave radiation with a Monte Carlo approach, where we follow from every grid cell a huge number of different rays in different directions to parameterize the backscatter radiation from clouds, for example, or if we are in a very deep valley or something like this. And this allows us, so this radiation transfer model together with the soil model allows us to calculate the energy balance at the surface layer. And therefore, we need a lot of parameterized input. For example, the land use is a very important parameter. For example, if we have more built-up cells in the city, or if we have vegetation, or which kind of surface type we have, if we have rock in the mountains, or if we have some crops on the field, or for example, also a water surface. This information is retrieved from the GCCP, so from our cloud provider, and is in the end provided by satellite information. And this is an example how this look like. For example, for one nest, this is the nest of Valencia, where you then can see that we have a kind of forests and the mountains, and we have the Mediterranean Sea, and we have these built-up regions within the city, and also this green kind of structure of this huge park in Valencia. And so this should give you an idea what the model is consistent of. And now I would like to show you some applications for the CityCLIM project. So what we do is we use this large eddy simulation model for a region of about 50 kilometer size in every direction. And we provide daily runs, so the model runs every day and provides a 48-hour forecast, so 2-day forecast for this region. So the model starts in the morning of a day, and then it takes a while, about nearly 1 day for the 48-hour forecast. But this is a very new approach that you run a model at this scale, a large eddy simulation model, on an operational everyday basis using such a GPU. And the 3 pilot cities within the CityCLIM project are the city of Karlsruhe, you can see here. So here's the city of Karlsruhe, this is the river of Rhine. And in the southeast, we have some hills from the Black Forest Mountains already. The second pilot city is the city of Luxembourg, which is presented in the center. So you have the city, and here you have this valley in the north of the city. And I think this is the river Mosel. And our third pilot region is the city of Valencia, already shown some slides before, which is a coast city at the Mediterranean Sea. And for those three nests, to provide such an operational forecast, we also need an operational forecast model chain. So we in our house, so at Meteorologics, we already run different kind of models. For example, the Europe Swiss HD model, which is a 4-kilometer model that runs every 6 hours and provides a forecast for a domain that is slightly smaller than Europe. You can see the domain in this image. And in this model, we have nested the so-called Super HD 1-kilometer model, which covers a region slightly larger than Germany. And it covers also the city of Luxembourg and the city of Karlsruhe. So we can use this model as boundary conditions for our 100-meter LES model, which you can see here. This is again the city of Luxembourg and the city of Karlsruhe. And such a model chain with the 1-kilometer model and an Ultra HD nest is also implemented for Valencia. I think we used also this 4-kilometer model because it covers the city of Valencia, and then we have a smaller 1-kilometer nest, and then within that nest, the Ultra HD nest for the city of Valencia. The daily maps, or even more than daily maps for the Swiss HD 4x4 and the Super HD 1x1 are publicly available on our website, karelmannwetter.com or meteorologics.com. And these Ultra HD LES ones are not there yet, but they are presented on our GCCP platform currently. So now I would like to give a short overview about the services we developed with the Ultra HD model within the CityCLIM project. We had three main kind of targets. One was the web-based presentation of the results of the Ultra HD model. That means we have a nice web browser-based app where we can have a map with an overlay of the prognostic fields and also can have a look at time series. Then we have these aggregation analysis and identification services, which is also a web-based service where we can make an analysis over a huge number of different model runs, because we have a model run every day. We can then aggregate these model runs and, for example, make a map with the maximum temperature in a certain time span or so. And last but not least, there's also the simulation and mitigation service where we can actually edit city aspects of the city model. For example, we can change the land use of the surface, or we can change the height, so the digital elevation model. And then we can rerun the model with the same boundary conditions and can analysis for a change within the model. And what I would like to do is that I would like to show you some insight in our web-based interface. For example, you can see the GUI is still a bit prototypical, but it's already working very good. So we have the heatwave information service where we can, for example, choose one of our pilot cities with the according area that is spanned there. And then we have a lot of these model ones where we can choose one that we are interested in, for example, the 29th of August this year. So the model ones go back quite about 1 year we have now with these model ones. But I will stick to this for the moment. Which one was it? 29th. And then we have different parameters. We have a temperature parameter with two different color scales. One is a very absolute, so those are both absolute color scales because our implementation currently needs that. But this color scale starts a bit higher. So here we have started with 0 degrees and go up to 40. And on the other color scale, we also have the colder regions covered. And then we have these, for example, the city of Karlsruhe in the middle. This is our model domain. And we have kind of an video overlay, so we can play the button and we can see that the time stamp is changing. So we are now early in the morning. The sun should get up every moment. We can already see that the mountains get heated quite a lot with the temperature. We have a slightly less temperature above water surfaces. And now we get near the afternoon, and in these structures you may get an idea on the actually mixing processes happening in the atmosphere. I will change to the other temperature scale with the hope that we see a bit more there. So you can actually see some gravity waves in the atmosphere. And now that the sun is the incoming radiation is happening, we actually have these convective structures within the boundary condition, in the boundary layer. The mountains are much cooler than the city. You can already see in this temperature the open heat island in a way. So the built-up regions within the city are much warmer than the surrounding. This is during the night. We have now getting some more fresh air from the northern east that is coming and flowing over the city. And you get such an video clip for every day for the last year in a way, with the actual weather situation around the city. Yes, another interesting day for the nest of Karlsruhe was the 21st, I think, of July. Let's see if this works now. We can also have a look at the surface temperature, for example, which gets very high during this day. We had a lot of incoming radiation, and then in the afternoon, something happened. You can see this. So the surface temperature reduced drastically in a way, and this is caused by some kind of a more deep convective event down to the south, which casts in shadow to the Karlsruhe region, and with that reduces the incoming surface radiation, and with that the surface temperature. This is also observable in the temperature field as well, of course. And is connected with some kind of cold pool of an convective event south of Karlsruhe. So these are the things we try to cover with this model. We can have a look also to the city of Valencia, for example. Some arbitrary day. I don't have looked for some special day, but so this is now, so you can see the air above the ocean is also very warm during this day. This is probably a pretty hot day in Valencia. And what we can also do is we can add such markers to our map. And then inspect, for example, different parameters where we have saved the numerical fields. It's not only the maps from the model, but also the numerical field values, so we can make calculations with it. This is an example where we now get, for example, here these 3 different measurements from the model. So we have a very warm center of Valencia during the day and some less temperature outside. So this is now the air temperature, actually, so the 2-meter temperature. We can also have a look at the surface temperature, of course. which then is the land surface temperature, which is the parameter that is often compared with satellite measurements or with airborne measurements and so on. Oh, this is pretty warm. Let's see if we can get some more contrast with this temperature scale. And in the model, this temperature is mainly caused by the different land surface types. So the build-up regions are a lot warmer than vegetation areas because the latent and sensible heat fluxes are different, and so another equilibrium temperature emerges at the surface layer during such heat waves. Another service, so this is the heat wave and information service, works an example. So you have a lot that you can look at, a lot of parameters. And another service is, for example, the identification service, which is used to make analysis on a longer time series of ones. For example, you could just as an example, you can choose one start point and an end point. You could cut out daily sections. So if you are only interested, for example, in the maximum temperature, it would be a good idea in the summer at least to restrict those daily sections to the afternoon, for example, from 14 to 16, something like this, or 18, and so on. And then here you can edit the sampling rate, which is the highest. So the actual model output is every 5 minutes, but then it takes much longer to produce this analysis. But I would recommend to always use the highest. And then you can select one of our output parameters and one operation, for example, the maximum temperature or the minimum temperature. We are currently also working in extend these operations with other kind of filters, for example, for the number of heat days during that period or so on. I won't start this now because it takes a while. I will just have a look in some examples. For example, we have here a map with the maximum temperature in Karlsruhe between the 7th and the 31st of August in the year 23. And then you get such a map with some features. This is still a bit preliminary, so it's a prototypical thing because this is also with model information from 1 year ago, and we of course developed that the model also, and so on. Yes, so this can be done with the identification service. And then the third thing was this simulation service, where we have this simulation editor, for example, also Cosmo, where we had some this editor, and you can change, for example, in polygons, certain aspects of the surface. For example, you could add such a polygon somewhere, and then you can say, okay, the new surface type should be tree cover, and the height should be the same as before. And then you could select a certain day of interest, which is one day where we save the boundary conditions for the model. And then you could request this model run, and then our backend will start this model run. This will then take a while, about 1 day for 48-hour simulation. And then you can take a look in the simulation service, for example. We did that for this day currently as a test. And you could, for example, see in the temperature that where we draw this, not this greenish thing, this was just for, but here this bluish thing where Ingo draw kind of a lake or a small pond in Karlsruhe. There we get a reduction of the temperature and of course always of the surface temperature, which is even more pronounced, and this should always have an effect on the surrounding air. But this is not very well observable at the moment. We are currently still working on that. One thing that is maybe from interest is also this pollution information service, which we implemented for the city of Valencia. And also we have a lot of model ones there. For example, in April, there was a quite strong dust outbreak. It was the 8th, I think. And we can have a look at this animation. So we can color scale already see that this is already polluted air around Valencia, and this dust comes from the south from the Saharan and is transported to the north and is then mixed down into the region of Valencia, where we then at the 20, no, this date is foggy. But then in with the further modeling one, so with the time that is running forward, we get this dirt mixed away, and then the air is again clean above Valencia. This is just an example of such an dust outbreak reflected within the UltraHD model and this web interface information service. So those three things I showed. We had this forecast and information service with the maps and our time series. We can do this identification, for example, with the maximum temperatures, and we can simulate changes in the land surface type, for example, and get results within the model. These are again some pictures to illustrate these three different services. Again, the heatwave information service, the identification service, and the simulation editor. And these are some images of a typical heat day for Karlsruhe. We already saw that in a way in the heatwave information service. So we have this land surface temperature that rises when the sun is coming up. We have the convection within the boundary layer, which reduces the dew point and increases the wind speeds. And then in the afternoon or in the evening, when the boundary layer is collapsing, we get higher dew points again, and we get this urban heat island around the city of Karlsruhe. And some further developments that we have in mind for the UltraHD model itself, besides the CityCLIM applications, we would like to improve the representation of the vegetation in the model and also the canopy layer itself. So we think about modeling the runoff, for example, of surface water in case of precipitation. We still have some work to do with the radiation model, so I would like to include multiple scattering also. Then beside these 48-hour forecasts we currently do with the model, we are thinking about going more in the short-range forecast or the nowcasting, so that we make very short forecasts, but quite often, so 12 once a day before 2 hours or something like that. That would also improve or enhance the effect of possible radar and satellite assimilation. And with that, we could then go into the live coverage of, for example, thunderstorms. And there we also think about building a model that has a moving nest, so that the model itself can move with, for example, a very strong thunderstorm or something like that. And it would be quite helpful, we think, in crisis management and things like that. And in the end, I would like to show this small animation we already also did to get an idea of the scales. So this is the city of Karlsruhe, and this is a 10-meter digital elevation model. So you can actually see the single buildings within the city. The now coming up green grid is the 1 kilometer model. So we have one temperature for one of these squares. And then if we continue, we can, or as a comparison, see our 100-meter model. So we have a much higher resolution than our 1-kilometer model and can represent structures like these forests or agglomerations of buildings or so on. But we are not in the region that we can handle like changes of one building or something like that. This is not the focus of the model at the current state. And we can also see in this animation that we have these ray traced shadows behind the buildings, especially then in the evening when the sun goes down again. And we also have this kind of Rayleigh scattering within from aerosols and water vapor in the atmosphere, which is a kind of this foggy representation. Yes, that's all for me for the UltraHD model. Any questions?
Thank you, Stefan, for the presentation and also for demoing those city climate information services. So we have a few minutes for any questions for Stefan. So we have one in the chat from Jonathan. How have you validated your simulation outputs?
Yes, so we have these heatwave information service where we have these kind of maps of the temperature. But what we also have is we have these our website, karelmannwetter.com, for example, where we have a huge amount of weather stations and so on. And what we do with the model is that we have an API link where we retrieve these weather stations that are available, for example, in the region of Karlsruhe. And those is on the one hand, those are used as kind of a simulation product. So in the beginning of the model, where we already have measurements, we can use that to fine-tune our state of the atmosphere during the initialization of the model. And then for the forecast region, we can, if the forecast is then done, and the day after, we have kind of a table where we calculate root mean square errors from these stations and also bias and so on. And with that, we have a validation of the forecast of the model.
There's another question here from Benjamin. Which information does the city have to provide, and are there estimates on how much does the service probably cost?
So what we need from the city itself, it depends a bit on what the city wants. So we have kind of a coverage, for example, of the actual land use or the digital elevation model from satellite, which can be used for the modeling. But for example, in case we would like to use higher resolution data, for example, this 10-meter city model we used from Karlsruhe, which is then also used to enhance the drag parameterization at the surface and so on, then the city should provide this higher resolution DEM. What it costs currently is
Yeah, we are currently working on the cost plan together with our partners from OHB, but the launching partner, because we're currently in the launching partner phase, would probably pay just one by one the costs that we have to actually run the model, because we are currently in the phase where we try to acquire. Oh, you don't see me, I'm sorry. That was just a shadow, a dark shadow speaking. Yeah, we're currently in the phase where we have to actually find out how to put these kind of things in business models. But for a launching customer, this would be one by one, one-to-one the costs that we have on hardware. And these GPUs, for example, to really run them, just the hardware on our side, that does not include the OHB side, who provide the whole web application and front end and the GCCP that Dr. Stefan Horn talked about. is about 1,000 to 2,000 euros a month.
Yes.
Yeah.
Thank you.
Thank you, Stefan and Miriam, as well for answering those questions. And Miriam Kakelman is actually next to present the Historical Climate Information Service.